Okay, take a seat, please. We begin the session. This is the second part of the Curiosity on Mars session. Just to recall everybody, we will have the third part of the session this afternoon at 1:30, and the poster session tonight at 5:30 in the red poster area. Just an announcement is that the last talk of this morning, supposed to be by Maria Paz Zorzano, has been cancelled, so we will have 5 talks this morning. And we will begin with the talk about the Curiosity Mali imager at Gale Crater, talk by Yingst, Edget, and a bunch of people from MSL team. And the talk will be given by Mark Lehman. Thank you a lot for coming here, Mark.
OK, thank you. I am Mark Lemon. I apologize that Eileen could not be here. That seems to be going around. I am a member of the Mastcam, Molly, and Marty science team, basically the camera team for the MSL rover. So I'm giving the talk for Eileen in that behalf. Molly is the Mars hand lens imager, the camera on the rover that's intent is to bring to us the fine-scale stratigraphy, geomorphology, and color of Mars. So as you see on the title slide here, the image on the right is a picture of Molly on Mars. Molly is on the turret at the end of the arm, front and center in this picture. The little pink area is reflecting from the bonding agent in the lens, so you see where Molly is there. The dust cover is open in this image, and you see a series of LEDs around Molly, and the rest of the turret instruments adorn the arm there. One of Molly's capabilities is illustrated to the left. Molly can focus. It can focus in down to 14 microns per pixel, or it can focus out to infinity. The closest we've come to testing that is star Alpha Eridani. But we use it in a mode like this where you get good context images from a perspective that even the lander cameras cannot get. And you show the rover itself, I should say the rover cameras, you see the rover itself in its context. So this is Molly. Molly is intended to serve as a geologist tool to give you Mars close up. And it was designed around that, one thing being at the end of the arm. It has a dust cover. Here the dust cover is shown in place with little windows. The dust cover also looks pinkish in there. It can image through the dust cover as necessary if it were to fail, for instance. It can shine LEDs. There are white light and UV LEDs. The UV are for fluorescence. The Molly itself is mounted on the end of the arm. So the Molly itself can see in color. It has a bare pattern, RGB pixels for the color imaging. It's about a 2 megapixel CCD mounted on the end of the arm with a vibration isolation unit provided by JPL, contact sensors provided by JPL so we don't ram it into a rock. And then the cabling provided by JPL goes through the arm into the rover, and I'll come to that in a moment. Also on the outside of the rover, on the shoulder joint, you've got the Molly calibration target, which provides color, grayscale for white balance, resolution, depth targets, as well as a US penny for scale. It's about 1.9 centimeters. Below that, you also see the APXS calibration target. Following the cables into the rover is the Molly digital electronics assembly. It does lots of fun processing. It can store the images. It can do focal merges. We can take images of a scene from the same position at a variety of different focus settings and use that information to create a 3D depth map of the scene, as well as to simply merge the images so that all of the image is in focus. So the early Molly activity on Mars is what I'm here to talk about, essentially what we've done for the first 90 or 100 sols. We're off to somewhat of a slow start. We got the first picture on Sol 1, which is an awesome picture because it shows that the dust cover did its job and was worthwhile to have. That is an image of the crater rim of Mount Sharp, or no, the crater rim of Gale Crater. I'm sorry, we're looking to the north, through a lot of dust. It was exposed to the elements on landing. The dust cover protected the CCD itself. This is an image with the dust cover closed about a month later, taken by the mast cam. The early activity is dominated by the instrument checkout, making sure MOLLE works, making sure MOLLE can be used, as well as helping other instruments. Support and documentation of first-time activities, which is rover speak for things that require a lot of deliberation before you do. Documentation and engineering support, and of course the science investigation. So the checkout activities include things like, here is an image of the remote sensing mast instruments, the mast cams there, the googly eyes, the ChemCam, and the navigation cameras. That's with the dust cover closed. This is the quality of image that we would be stuck with if we could not open the cover. From this point onward, 32 sols into the mission, 32 Martian days into the mission, we were able to image with the dust cover open. So you see the calibration target for the APXS imaged on Mars. You see our calibration target imaged on Mars with its color targets and resolution scale and US penny. Imaging of the front HAZ cams as part of a general survey of the undercarriage of the rover, and I mentioned the remote sensing mast. Support of first-time activities, making sure that we can proceed with things we really want to do. MOLLE was used to help check out the driving system of the rover. For instance, in looking at the wheels, as you can see, by the time we could image the wheels with MOLLE, we'd done some driving, but we were able to check out the entire undercarriage and check out the status of the wheels. MOLLE was used to check potential scoop samples. Here we are at the Rocknest site. This is Rocknest. This is the Rocknest sand shadow. The desire was to put fine sand through the sample handling system as part of a decontamination. So MOLLE was used first to check out the potential samples themselves, to see if they're suitable to go through the sample handling system in terms of safety and in terms of having proper grain sizes. So you see the set of samples that we acquired taken from MOLLE. One thing you don't see in this picture is MOLLE or the arm that holds it. The picture was made by a few dozen individual images of MOLLE, basically holding the camera out with a robotic arm and moving around such that you could put them together without the arm being in the way of the camera at all. So there's everything but MOLLE in the arm instruments. Let's see. And there's, of course, Aeolus Mons in the background. And there's a wheel target where APXS is used in just a few slides. So MOLLE is also used for documentation and engineering support. You see here the topographic meshes that can be created. MOLLE can be placed side by side for stereo imaging. And this is two targets in the Rocknest sand shadow area at then in Burwash. And there is the rover wheel for scale. So the topographic meshes can be created from the stereo images, imported into planning software, and used to plan further things like, for example, APXS contact or sample acquisition. MOLLE is also used for engineering targets of interest, in this case, something that we saw from the remote sensing cameras, and then later saw specifically in the Rocknest sand shadow area as something, as a possible hazard, including as something that blew into our trench, was foreign object debris. Some stuff here that's really not Martian. It's alien material. Unfortunately, a spaceship blew up about a kilometer or two away from here when our descent stage crashed, and a lot of Kapton tape, foil, and other stuff is floating around the general area. So we had to make sure that did not go into the sample decontamination system. MOLLE was able to carefully inspect things before and after scoop samples, as well as we had the ability to hold the scoop up to the mast cam to see what was on the top of the scoop. The documentation and engineering support included things like looking at potential sample material or things that the APXS could look at. So there you see the imprint of the APXS on the wheel track within the sand shadow. In addition, MOLLE would be used for getting images of things that were about to go into the analysis instruments on board. In addition, MOLLE can be used for range finding. So when you're going to take a scoop or going to place the APXS and you want a precision placement of the APXS, you can use this camera on the end of the arm to get the stereo data that you need to know exactly where the arm location is with respect to the surface so that you can sample immediately thereafter. So the science investigation for Mars is, or for MOLLE, is to look at things at the finest scales, as well as to provide context. So that science investigation got started after those initial images with the dust cover closed, somewhat in parallel with some of the support imaging. So here you see on Sol 33 our first image of Mars with MAHLI. This is looking down. Here you see a scale bar looking down at Mars just from a standoff distance before we could actually approach closer. MAHLI, of course, is at its element when it can zoom in and give us what we want to see. So what we want to do is get the finest scale stratigraphy, look at the texture, look at the color, look at the morphology of things down at the tens of micron to 100 micron scales. So here you see an example of how a MAHLI investigation proceeds with at the outside a Mastcam 34, the medium angle camera for Mastcam, looking at the rock Jake Matijevich. So you've got an overall context, and then you have MAHLI placed such that, placed 25 centimeters from the rock, such that we have about 100 micron per pixel resolution on the rock itself. And right there you've got our penny for scale pasted in from one of the calibration target images. Then MAHLI was moved in for successive distances to get down to 23 microns per pixel. And then in the yellow here, you see where some ChemCam shots were taken as well. So MAHLI provides the context as well as the very close-up imaging. So the close-up image is shown here, as well as the nested images for scale. So you've got 100 micron down to 32, down to 23 micron per pixel. We can get down to 14. We have not exercised that yet. That requires much care to get the MAHLI that close to something. But of course, we do have our contact sensors to prevent damage. So in looking at the rocks with MAHLI, we've had several examples so far in the rock nest area. You have here the rock Bathurst at 22 microns per pixel. A nice thing about this is in this in-focus area at the front of the rock here, you can see the individual sand grains that are on top of the rock. So this is stuff that is saltated around and has been left sitting on the rock. Going off to Burwash, this is a focus merge. As I mentioned, we can change focus as we take the images. We've got a fairly narrow depth of field, but the images can be stacked and put together such that you've got a wider range of focus. So there's about a 10 centimeter look at Burwash. We see many different rock surfaces. That diversity increases after this first 100 sols that we're talking about right now. The soil imaging was prominent in this time period because of the investigation of the rock nest sand shadow. So you see here a look into the wheel track itself, unconsolidated material, mostly dominated by sand that is dust coated. And then you also see larger grains in here up to millimeter sizes, many of which also have little dust coatings, some of which have rolled around and are not dust coated, showing the diversity of color. You see grays and reds up to nearly white. You see glassy things as well as translucent and more pale objects. So there's a diversity of objects within that scene. Then we were able to put the material through the sieves within the arm and dump them on an observation tray on the rover itself. This is what we have to look at a 21 micron per pixel resolution. So we're looking at things that are in the 100 micron ballpark. They've gone through the 150 micron sieve, basically showing that there is material that makes it through the sieve and characterizing that, in fact, it is the size that we expect and looks somewhat representative of the stuff in the background in this image. So we looked at the soil characteristics in a broad sense, and you can see here an investigation into the wheel track itself, into the trenching itself. So the first scoop went into the rock nest sand shadow here. There's part of our shadow overlying the image. And then you see the features within that scoop, including this little collapse feature and the material at the bottom. So working down, we've got these millimeter scale surface grains that are highly dust coated, forming a crust. So the dune has not been active recently. It's dust coated, and the dust is pervasive in the top surface. In fact, there's a several millimeter area here of crust. Then you get down to this unconsolidated, very fine-grained fraction. You have the possibility of subsurface layering, as you see in here, dark, white, dark banding, which could be a sampling artifact, or it could be actual layering. That's something that there are diverse opinions on. And then here's a broader view of the scoop surface, including one of the foreign objects of concern. This is our third scoop target. So it gives an overview, the 4-centimeter wide scoop. Again, you see the possible banding. You see the crust as it is broken. Clods fall off down into the scoop, or down into the trench itself. And then you see, as the scoop pulled out, the fine material from underneath flowed freely and eventually came to a halt and bang on some of these larger grains on the outside on the crust itself. So I'll stop here and just remind you that MOLI is the tool for looking at Mars up close with MSL. It's there thanks to a broad group of people, the engineers who put it there, the engineers who operate the arm and allow us to be up close, as well as to the science team and the MOLI science team for operating this. So thanks to all of them. And I'll remind you that there is an open access paper available on this with plenty of details on MOLI and its workings, written by the PI, Ken Edgett. So thank you.
Questions for Mark?
That was a fascinating talk and spectacular images. The image that you showed of the soil on the left-hand side and then on the right-hand side, the material that had gone through the 150 micron scoop, I think I remember seeing, was that presented at EGU in the sort of live press conference?
Yes, I think this was the EGU.
Because I can't remember, I don't think anyone asked. One of the things that really fascinated me when I saw this image before was the glassy material, the ellipsoids and the spheres. Do you know if anyone's got any idea of what those actually are?
I know that people have been tossing around ideas with respect to those, in particular the rounded and ellipsoidal glassy things. Certainly could be volcanic or impact related, but I don't think we can say that they have to be from the image.
Okay, thanks.
No more questions? So next talk is going to be given by Violaine Sauté. She's going to talk about igneo composition variation by ChemCam.
Hi, so I'm going to give you a compositional overview of rocks along the Curiosity Traverse using ChemCam instrument, which is located at the top of the rover mast. So I would like to remind you that this laser is the first laser ever sent outside the Earth for extraterrestrial purposes, and such an achievement had been possible thanks to the huge amount of work between French team and an American team, gathering at least 200 engineers and researchers. So the outline are quite simple. First of all, I will describe ChemCam instrument briefly. In a second part, I will show you the traverse map and how it's possible to distinguish on the lithographic and textural rocks argument two different zones, Bradbury landing site first and then rock nest area. Then we will see the compositional variation along this traverse, precisely between these two zones. And finally, I will summarize the most outstanding result we get thanks to our analysis with ChemCam instrument. So ChemCam basically is a combination of two instruments, a laser-induced breakdown spectrometer, LIBS, associated with a remote microimager, RMI. So this laser is able to measure very, very rapidly elemental composition up to 7 meter distance from the rovers. It's measuring essentially major elements, but it is good as well as measuring hydrogen, lithium, beryllium, boron, carbon, nitrogen, and oxygen, but it's not really good at measuring sulfur or chloride and phosphorus. The laser beam size varies as a function of the distances, and it's range between 350 to 550 micron. At each observation point, we have between 30 to 50 laser pulses that allow us to remove the dust of the sample and as well to do some depth profiling, allowing us to detect eventual alteration crust. And finally, the RMI provides context imaging with a very high resolution. Between and among the 17th camera on board, it has really the greatest resolution, 50 microradian. So, starting from Bradbury landing site, which appear in dark here, which was due to the descent thruster, the Curiosity rover moved east 500 meters down to Glenelg Triple Junction. So during this traverse, at least we can differentiate two big areas. The first one, the longest one, we call it Bradbury site. It's approximately 400 meters. And the second area, called Rocknest area, it's sandwiched between this large area and Yellowknife Bay, where the rover is actually stationary there. And you see in white all the ChemCam target that we measure during the traverse. So it's around 50 ChemCam target, which means 340 points, which means even more than 10,000 laser shots. So the Bradbury zone, it's defined by this kind of landscape. You have a lot of floats rock, loose rocks that are disseminated over discontinuous outcrop. These outcrops are essentially alluvial and are made of conglomerate. And you have here link conglomerate where you can see rounded pebbles, black and white pebbles. So those are alluvial. The floats rock are essentially igneous in origin, and you can distinguish different categories. Here you have, of course, effusive rocks, where you could see clearly feldspar lath. You have fine grain rocks like coronation. You have coarse intrusive rocks like torlex with millimeter-sized granular minerals. Then you have stark, which is another type, which is some sort of scoriaceous whitish rocks, and some banded rocks. So then when you pass to Rocknest area, it's a completely different landscape. You can see here that rocks are stratified. Here you have dark layer interbedded with some whiter and flatty material, showing some polygonal features. And if you look in detail to these rocks, they are really very fine grained. You have this kind of rocks, very fine grained, dark rocks with sandstone-like texture. Or alternatively, you have this kind of rocks with agglutinated blobs and spatter. So interestingly, to summarize, before the transition, soil are very coarse grains. They are gravels, and there will be a talk this afternoon dealing with this soil analysis with ChemCam eyes. And so to remind you that the ladder beam of ChemCam is of the order of 500 micrometer. So if the grain size is very coarse, obviously you will analyze mineral composition rather than wool rock composition. Then when we pass in Rocknest areas, the soil is changing. They are very fine grained, Aeolian ripples, and rocks as well are very fine grained. So with ChemCam, we will more likely analyze wool rocks composition. So let's look at the composition that we measure with ChemCam. So in the first part of the traverse, so it's in the left-hand side of this figure, you see this is a traverse with silicon elements. So what you can see, you have a lot of variation with respect to silicon content, from low silicon to high silicon content. So, this high silicon content correlates with high sodium content, high aluminum content, and can be easily attributed to feldspar kind of minerals. These feldspar minerals, you can see them very clearly in this kind of rocks. Now, if you look at the low silicon composition, some of them correspond to olivine, like firelight, with a low Mg number. Other points correspond to orthopyroxene. And in between 40 and 50% silicon, you may find rocks composition as soon as the rocks are very fine grained, so that ChemCam is able to sample a whole rock composition. So to summarize, we find feldspar-like, olivine-like, orthopyroxene-like composition for minerals investigation. For rocks composition, two kinds of rocks were distinguished. Rocks that are highly alkali basalt and with maybe tephrite, and APXS did a measurement of these rocks, this kind of rocks, which was called Jack Matichevit, which is a meteorite. So those are one kind of rocks. You have other kind of rocks which are noritic in composition, coarse-grained rocks, so very different origin. So next, when you pass in the second zone, what you could see in rockness area, the composition are changing. So the silicon composition average value are lower compared to the first part, and they are much more concentrated value, which just reflect the fact that we are targeting very fine-grained rock. And so rather than targeting independent mineral, we are targeting wool rock composition. But the outstanding feature is that these wool rock composition are slightly silicon poor compared to the first part of the traverse. They are as well aluminum poor, but they are much more iron-rich. So you have this iron-rich concentration, which is really the signature of rocks in the second part of the traverse. Here you see as well crystals that are devoid of silicon and which are mainly non-silicate phase that have been tentatively attributed to some sulfate phase mineralogy. So if you look more in detail, here is Bathurst rocks. So it had a sandstone-like texture. And APXS measurement on these rocks show clearly it was a basanite. And we have the same kind of diagnostic with ChemCam instrument. Another rocks here is rockness rocks. So here you have all the ChemCam points that had been analyzed. So at this stage, we are still processing the data, but at first inspection, it could be an accumulation of olivine iron-rich mineral and oxide phases due to some sort of gravity sorting, but these data are still in process. So now, to summarize the chemical data on a simple diagram, here you have sodium versus potassium. In the first zone, rocks are much more sodium-rich, and in the second zone, the rocks are much more potassium-rich. So to summarize, it's very interesting because we have been on Gale craters since a few months now, and the variety of rocks composition is outstanding, just comparing with MER result obtained in the previous mission. So in the first zone, we could find effusive kind of rocks, such as alkali basalt, which are sodium-rich, magnesium poor, which is a very important feature of Gale crater so far, and rocks like tephrite and meteorite. You can find as well coarse-grained intrusive rocks with some compositions that are akin to noritic rocks. And this could corroborate recent orbital observation of feldspar-rich area and class since in the New Breccia, the meteorite NWA7034. So this norid kind of composition could be indication of crystal ancient primitive crust that would have been sampled in this area. So in the second zone, we find a completely different kind of association. So the rocks are finer grain. They are very enriched in iron, up to 25%. They are potassium-rich, silicon and aluminum poor. So some of them are basanite. Some other could be mixture and concentration on phthalate and oxide minerals. Inside the MSL team, at the moment, there is a big debate to know whether this kind of rocks in the second part of the traverse are volcanosedimentary in origin or purely sedimentary rocks. So to summarize, most of the rocks we did analyze so far have no coating. We were able as well to measure trace elements like rubidium, strontium, and barium, which allow us to classify the feldspar kind of mineralogy we analyze. For instance, strontium are much more anorthitic type of feldspar, whilst barium are much more potassium-rich type of feldspar. And we may say we may find the first intrusive felsic rock and analyze them directly on the surface of Mars. So thanks for your attention. Okay.
Thank you very much. Any questions?
Do you have any evidence, such as shock features, to suggest whether your intrusive rocks have been brought to the surface by exhumation in an impact, or whether they've been brought to the surface by exhumation and erosion?
At least it's difficult to see that with the RMI so far. Maybe we have one rock, Mara, that could have some trace of impact processes, impact melt, but so far we are not yet able to say if we really identify the melt pocket and things like that that could be attributed to impact processes.
Okay. Any other question? No. So thank you very much, Violaine. And next talk will be given by Susi Latreja. He's talking about MSL SAM measurements of known condensable volatiles.
All right. Chris Webster was left out from the abstract unintentionally, so I've added his name to this. Actually, I'm really reporting on behalf of the entire MSL team. It's a large team, as you heard on Monday, and we work together. And so far, we don't have any fights, which is great. So the purpose of my talk is to give you a feeling for the non-condensable volatiles in the atmosphere of Mars that we measured with SAM. SAM is the instrument that you don't see here. It's located in the underbelly of the rover. Only the feeding tubes are sticking out, and that's where we take in the atmospheric sample and the solid samples. On Monday, Patrice Cole talked a great deal about the instrument itself, and I'm going to focus on the composition of the atmosphere, in particular, the non-condensable volatiles. So the first thing is, what are the non-condensable volatiles in the atmosphere of Mars? Well, all the noble gases are non-condensable. Primordial argon, krypton, xenon, helium, neon, they're all non-condensable. But their abundances are low, on the order of 1 part per million to be, and less than a tenth of a part per million. And so they are very difficult to make measurements of. So if you're looking for seasonal changes, it's not these primordial gases we want to go after because they are small. We have to do enrichment in order to be able to even detect them. And then if you want to study the seasonal changes, then it's a special experiment, and it's not very practical to go after them. Oxygen, we can monitor all the time, but it's chemically reactive. So it's non-condensable, but chemically reactive. So again, it's not a good candidate for studying seasonal changes. Methane, we do not have a definitive detection of methane at the surface of Mars. The upper limit is 2.7 parts per billion. But even if we detected methane, the amounts are small, and the fate of methane is controlled by its various production and loss processes, and also the storage and release over time. So even if we detected methane, this is not going to be a good candidate to study for the non-condensable seasonal changes. On the other hand, these things in bold are very good. Nitrogen, for all practical purposes, in the homosphere that is below approximately 120 kilometers, is well mixed and is inert. And so this is a really good candidate to study the changes with time, with seasons, and so on and so forth. Radiogenic argon, 40 argon isotope, that comes from the decay of potassium-40 in the rocks, has a half-life of 1.3 billion years. So it's in the atmosphere, and this is an excellent candidate to study the seasonal changes, temporal changes, and so on and so forth. And so is carbon monoxide, because the photochemical lifetime of carbon monoxide is long, 3 years. But it varies, of course, with seasons, and so will these other things, which I'm going to talk about. Now, why do we care about the abundances of the non-condensable volatiles? First of all, they provide a reference. Today, you want to know what the composition, exact composition of the atmosphere is. You can then use this as a constraint in the models of the evolution of the atmosphere. The ratio of argon-40 to nitrogen is also used to assess the degree of mixing between the internal gas component and the atmosphere that's incorporated in the shock melts of the SNCs, the Martian meteorites. So it's really important to know the composition and the composition of the non-condensable volatiles in the atmosphere. The measurements were carried out with the SAM quadrupole mass spectrometer. And this is a typical spectrum on Sol 45. We're around Sol 232 or maybe more at this time. So this was at the beginning, but we carried out these measurements time and again over many, many months. So this typical spectrum of a portion of the mass spectrum, because we go up to over 500 mass numbers, and this is the mass to charge ratio here, shows the carbon dioxide fractionation pattern. So you're seeing here the carbon dioxide isotopes, carbon dioxide main peak at mass 44, and then you're seeing at mass 28 carbon dioxide going into carbon monoxide in the mass spectrometer, and then so on and so forth. Likewise, you see the signatures of nitrogen here. That's the mass fragmentation of nitrogen at mass 14. That's doubly ionized nitrogen, and so on and so forth. So we have these spectra for many, many different sols over which the measurements were done with the quadrupole mass spectrometer. The results we get for the atmosphere of Mars above Gale crater and their comparison with Viking is shown in this chart here. And when you look at this, the carbon dioxide, what we're measuring in this orangish bar here, is 95.97% by volume of the atmosphere, whereas Viking measured 95.3%. Argon is larger than what we measured. It's about 21% larger. It's at about 1.93%, and Viking was 1.6%. in the Viking observation, nitrogen was the second most abundant gas at 2.7% by volume. And we're finding it to be about 35% smaller in abundance compared to Viking. Oxygen and carbon monoxide, they're very similar in abundance compared to Viking. They also vary seasonally, so these are comparable results when you take into account slight changes relative to the observations that I'm going to talk about in a moment. You'll say, well, what's the big deal? There's 21% here, 35% there. They may be all about the same. The big deal is actually here. It's the ratio between argon and nitrogen. So indeed, the fact that argon is just 20% or so, 21% larger than Viking, nitrogen is about 30%, 35% lower than Viking, that's in itself is an important result. But the ratio of argon to nitrogen is very different. And it's the ratio that's important. Argon is inert. Nitrogen, for all practical purposes, in the part of the atmosphere we are working in, is inert. The ratio of argon to nitrogen should not change from Viking to SAM, to MSL observations. So the same information is in this table, plus some more. And I want to point out a few things here. First of all, the measurements of SAM for nitrogen and argon, they have very small error bars. Now, these error bars are slightly larger when you see this science paper or the paper that we are working on come out. You'll see slightly larger error bars. They're not all that much larger. They change by about a few % at most. But they're extremely solid measurements. From one measurement to the next measurement and so on and so forth, the results are rock solid. You just get the same results every time with very, very small error bars. So that's one good thing to note. The other thing, of course, I pointed out that the ratio of argon to nitrogen is 70% greater that SAM finds compared to Viking. Now, if we look at the observation geometry, which is here in the last 3 columns, the SAM measurements were done at Gale Crater, of course, are being done at Gale Crater even now. And they're essentially equatorial because Gale Crater is at 4.5 degrees south. And it was the time of spring when we did the observations. Whereas the Viking observations were done in the northern summer at mid-latitude, 48 degrees north. What is important is the surface pressure. The surface pressure is not all that different. At the time of Viking observations, the surface pressure was 7.6 millibar, and it's ranging between 7.7 and 7.9 millibars. So when you're talking about mixing ratios, the relative abundances, you're essentially taking the ratio of the abundance of the constituent, like argon, to the rest of the atmosphere. And the rest of the atmosphere, if it's not condensing, is essentially carbon dioxide. So the fact that the Viking observations were done in the summertime, mid-latitude, and the SAM observations are essentially at the equator in the spring, the pressures are about the same. You don't expect the mixing ratios to be all that different. But they are different. So let's look at some of the observations that have been done in the past. And a good example is the observation of argon that has been monitored for quite some time with the gamma ray spectrometer on Mars Odyssey spacecraft. And those are results that were published by Anne Sprague. She wrote a very nice review of this recently, covering 3 Martian years. And the important thing is that the argon mixing ratio at the southern pole increases by a factor of 6 compared to the value at the equator. So the GRS, the Gamma Ray Spectrometer of Mars Odyssey, doesn't really measure argon. They reference it to the Viking value. So they can say what the relative change is, and they find that it increases by a factor of 6 over the southern pole in the wintertime. And that's understandable because on Mars, carbon dioxide condenses over the southern pole 7 trillion tons of it condenses every year and goes into dry ice onto the southern pole. And the same kind of process occurs in the northern pole with water ice as well as carbon dioxide ice, but to a much lesser extent. And these are the data for the equator. And at the equator, according to these observations, there's really no change. The average of this over 3 Martian years, between 15 degrees north and 15 degrees south, it doesn't show any seasonal change. But it's really controversial data. Because at the same time, we have observations from Mars Exploration Rover Opportunity, MER-B, with the APXS instrument on that, and it shows that there are seasonal changes in argon. I'm showing you these data in a little bit blown up figure here, same data from APXS. And these data were sent to me by Steve Squires, who is the person behind this with his team. And these are the pressure changes. And these data came from Vikings because there's no measurement of pressure on APXS. And these are the argon data, and these are counting rates actually, essentially. So if you see the changes here, they're kind of tracking the pressure changes. And this is all equatorial because MER is essentially in the equatorial region. And it says that the argon mixing ratio actually tracks the pressure almost literally with a time lag on the order of a few months, which has to do with the general circulation. So that's contrary to what we saw in the case of the Mars Odyssey data, which indicate that there are no seasonal changes seen in the equatorial region. But you have to understand that when you're working with the orbital data, Mars Odyssey data, they're not all that accurate when it comes to making measurements of low amounts of argon, which is what we see in the equatorial region compared to the polar regions. But the APXS data are really good. They're sitting on the surface of Mars, and this is an actual spectrum that was taken off the atmosphere. And you see a clean argon line at approximately 3 kilovolt, kilo electron volt. And the background is really low, so they can actually monitor the argon really well with the APXS. We see a similar behavior in carbon monoxide. And this kind of observation was done many years ago with Mars Omega. Thérèse Ancanas and colleagues published those results. This is a result from recent MRO CRISM data, and they show seasonal changes in carbon monoxide. The change is on the order of about a factor of 3 in the southern polar region, and the top part actually shows the data. This is smoothed, but it's the same kind of behavior that you're seeing, the seasonal changes in carbon monoxide. So argon, carbon monoxide. What about nitrogen? Unfortunately, we do not have any data on the seasonal change of nitrogen so far. And so this is my actually last slide, and we're going to be monitoring monitoring the nitrogen with SAM. What we have shown so far is that we can take these measurements of the composition, and sol after sol, we're getting rock-solid results. They're repeatable, and the results I showed were for the first 90 sols, actually 100 sols. The Viking data, on the other hand, were average 3 days out of 6 in the first 6 days of operation. 3 days of the data, there were actually 3 data points, and that was just the average of the 3 data points. So we got a lot more data that we have from SAM. The results are really good. They're repeatable. And the technology that's being used in SAM mass spectrometry is, of course, the state of the art. We're doing it now as opposed to what was done 35 years ago. We need to monitor nitrogen. We have shown that we can measure these non-condensable volatiles, including nitrogen, really well. And we are going to be monitoring nitrogen. I think the next experiment is coming up within the next, well, after conjunction, very soon after conjunction. we'll be doing the measurement of the atmosphere again. We're now in the summertime. All the observations I showed you were in the springtime, and we're going to be making the measurements, of course, of nitrogen, argon, carbon monoxide, and we can see how things are changing from spring to summer. And with that, we'll find out whether the nitrogen to argon ratio of 40 argon to nitrogen ratio remains constant as we expect, or it doesn't. And if it doesn't, then we have a lot of thinking to do of what's going on, because these are inert gases and they should not change from Viking to now or pretty much any other time. So I'm going to stop here and leave it up to you.
Thank you, Sushil. Question from?
Yes, I want to ask about the difference between Viking and Curiosity data. But in case of gamma spectrometer data, is it possible that the altitude dependence may be the factor which make a difference between the gamma ray spectrometer measurement, which is a column density through the whole atmosphere, and surface data from APXS? So it may be some possible altitude-dependent effect.
Yeah. Just to be sure, Igor, you're talking about Viking and...
No. I'm speaking about difference between the APXS measurement and for argon and gamma ray spectrometer measurements for argon. First data is on the surface, and orbital data is integrated amount through the atmosphere.
Yeah, that's a good point. I mean, there's a lot of discussion about the Mars Odyssey data from orbit versus the APXS data from the surface. The mixing ratios in principle should not change, but both the Odyssey team as well as other people independently recognize that with the Odyssey, when you're actually looking at the relatively low amounts of argon, which is what you have in the equatorial region compared to the polar region, that the signal to noise really goes way down. And so actually, let me go back to the slide and I'll show you something here. So it's the grand average of all these data points that gives you a value which is essentially the same as the Viking result. But you see there's a lot of scattered in the data here. And if you're talking about changes on the order of 20% or so because of the change in the pressure, it could very well be in there. It's, when you average it out, it just averages out to about the same as the Viking value. And so it may be just because the orbital data do not have the kind of signal-to-noise ratio when you have the low amounts of argon in the equatorial region, as APXS people pointed out, others pointed out. But when you're sitting on the ground, you're making this measurement, as a clean measurement of the 3 kilo-electron-volt line. You can't be wrong.
Jeff Cargill, University of Arizona. Just in case you end up deciding that there is seasonal variation in that mixing ratio, have you ruled out the possibility that argon might be condensable as a minor constituent within CO2 clathrate?
Yeah, that's a good point. We're talking about equatorial region, and the amount of the CO2 clathrate that you're going to form in the equatorial region pretty much any time is going to be minimal. So, South Pole, yeah, of course, yeah. In South Pole, you see big changes. So, but we're talking about equatorial region, so I'm just comparing the equatorial argon results from previous measurements versus the equatorial argon results from SAM. So in the South Pole, yeah, it's a possibility.
Okay, we move on to the next talk. Our next talk is by Bob Alberti and colleagues from the RAMS team and the MSL team, and the talk will be given by Javier Martin Torres, sorry.
Thank you very much. Well, I am not Bob Howley. I'm Javier Martin Torres. Bob Howley wanted to apologize. He was sequestered by NASA, so he was unable to come to the meeting. But he didn't want to pass the opportunity to present the data from REMS on pressure. I think we have a very nice data set of pressure measurements. And this is why I'm here. He wanted to acknowledge all the REMS team and, of course, the MSL science team. Well, you know all this picture. I mean, this is the self-portrait of MSL. REMS is not an instrument that is located in a single place on the Curiosity rover, but it's located in several places in the mast. We have two booms measuring the humidity, air temperature, wind, and then we have a UV sensor on the rover deck, and then we have the pressure sensor here on the deck too. Well, this is a slide from Bob, but I think everybody knows what is pressure, but just in case, you know, it's the weight of the air column about the unit area, and of course this pressure is going to change very much with elevation, with winds, with source and sinks. And well, REMS is having a very big data set. I think the better and more comprehensive data set of pressure that we had to now, and we expect to have much more data. So we are seeing information that goes from seconds to years in timing scale, we think, and we have observed some new phenomena that we think that had never observed before in Mars. I will go in detail in the next slides. And in increasing time and space scale, these are the features that we have been observing, vortices, dust devils. We have seen the crater circulation, and then flows of winds and circulation of air. We've seen the flow of air coming around the crater and then descending to the crater. Global circulation component like thermal tides. We've seen, especially after Sol 90, we've seen dust loading in the atmosphere with the affecting pressure, temperature, and other variables measured by REMS. We are seeing the seasonal CO2 cycle. We see that how the solar cap is still emitting, and then we see an increase in the pressure over time since the beginning of the mission. Then this is something that Bob is an expert on, global mass balance, and it's something that he wanted also to point here. And then he says something about distribution of water ice in the ground. He thinks that we can give information about that, and you have to trust him. So if you have questions about that, probably he should be the person to contact. I can give you the email address if you want it. Well, I'm not going to go into detail of this. Well, this is the pressure sensor has two barrier caps, but we're going to have a poster on pressure. Probably Ari Matti is around here. I don't see him, but he will explain much better than me how the pressure sensor works. I would like to point out the performance. We have less than 3 Pascal accuracy, which is very good because we see many features that are in that ballpark, and are very interesting that I have never seen before. We see, there is a 0.2 Pascal precision, and we have a stability of less than 1 Pascal per year. This is a figure showing all the pressure data from the Sol 9 until Sol 100. You see that there is an uptrend on the pressure, the blue measurement, instantaneous measurements, and the daily averages in red. You see that there's a clear increase on the pressure since the beginning of the season, as we expected due to the season that we are and the sublimation of the polar caps. This is something that Bob has called the heartbeat of the climate system. We see that there is like a kind of a heart beating, and this is from Sol 60 to Sol 63. So in these 3 sols, we have the increase and decrease of the pressure with time. Nominally, REMS was measuring every 5 minutes. 5 minutes per hour. During the day, and then we had an extended hour measurement. But with time, we have
being able to get more data. So more or less we have around 5 hours per sol of data. And the daily variations, I think they are more or less as we expected, around 85 Pascal, with a maximum of the pressure around 7:30 a.m. Local Martian Standard Time, and around 4:30 p.m. local time minimum. And this is something that is very much repeated over season, and I think this is a composite pressure. Taking into account all sols from the beginning of the mission until sol 100. Then, well, he's presenting here that the signature of when we see vortices, we have seen many vortices during during operations, and we see that the features are very similar with the changes in pressure, drop in pressure, and increase in temperature that were seen by the Pathfinder or Phoenix instruments. We think that the pressure, the delta pressure, I mean the changes in pressures are a bit smaller than the ones that we saw in Phoenix. But this is something that we are investigating, as this is too. I mean, this is an evening oscillation that we see nearly every sol. We see like an oscillation around evening, around night, local time. And this is something that, Bob thinks that could be gravity waves. This is something that we are still debating. And, but it's something that we think that has never seen before in Mars. This is a comparison between the Mars-Worf general circulation model and REMS pressure data, different color for different sols. I mean, you see that more or less the features are repeated nearly every day. And with the maximum around 7, the minimum around 4:30, 7:30, 4:30. And then there are some features in the data that here that are not reproduced, at least by Mars-Worf. I guess there are other models, for example, the MRAMS model of Southwest Research Institute that does produce these features here. So it's not clear for all teams also that this is a crater circulation signature. It could be something that is just due to daily variations. This is under investigation too. But there is a paper that was just published by Taylor and Barnes, where they think that these features that we see in the morning and in the evenings are due to crater circulation signatures. Well, here is we see a diurnal tidal as were seen by the Viking landers. It looks that there is a decline in the Kelvin wave. We see clearly the dust storms. I mean, we see an increase in the amplitude with dust storm. That's something that we were expecting. This is for the phase. In the phase, we also see a change when the dust storm happened. And this is this is an effect of the tidal. Of course, when there is a change in the dust law of the atmosphere, there is a change in the pressure too, and this change, it has an effect on the tidal signatures. Here, there are data from Mastcam. There are optical depths in blue. Probably they are given by Mark Lemon. I'm sure the Mastcam optical depths. They have some MER data and Themis data. I don't know who provided them, but we see that there is a correlation between the tidal amplitude and the optical depths that we have in the visible and in the infrared. The semi-diurnal tidal amplitude here. We have some data from global storms and from Vikings. We saw an effect that was not exactly the same that we are seeing in the storm now, but here we have a regional storm, and probably the physical processes involved are a bit different. This is a figure of there was around Sol 96, there was a
dust coming from the north that was deposited around the area of the rover. We see many features in the REMS data, not only in pressure, but in temperature, in the ground temperature, air temperature. We're seeing many effects related with this storm. We have seen change in opacity very clearly in the UV sensors too. And here you see a comparison between the pressure measured over the first sols here in MSL, from the first 100 sols, and compared with the measurements by the Viking 1 in red and Viking 2 in green. There is a better agreement between Lander 2, but when we extrapolate the data to the gale, pressure, and conditions, we see that there is it looks like what Bob's calling a decadal climate change. We don't know. It's like a decrease in the pressure, and well, we are in different seasons too. So this is under investigation too. And here is a summary of the data, where we see that the pressure data reveal information on many different scales in space and time. Some of the new phenomena that REMS is observing is relatively dust-free convective vortices. We see vortices, but we don't see dust. So it looks like the vortices are not strong enough to lift up the dust. So up to now, for example, in the UV sensor, we've been able to detect 2 dust level candidates, but they were not very strong. We see evening oscillation, the ones that I showed you at 8 p.m. We also see some oscillation around 5:30 p.m. Just right after the sunset. We see the crater circulation, of course, due to the topography of Gale. I mean, it's a big crater with big walls. I mean, it's to be expected to have a lot of circulation that is dominated by the orography. And then we have some familiar phenomena from previous missions, like thermal tides and CO2 cycle. And of course, well, the things like the global mass balance needs more analysis, and we need more data as the mission goes on. Thank you for listening. Thank you.
Thank you. Come on the mic.
The surface pressure is dependent on the elevation of the surface, and if the rover moves from one place to another place, which has another elevation...
Sorry, I can't...
the surface pressure is dependent on the elevation of the surface.
Yes.
And if the Curiosity moves from one place to another place, which has another elevation, this effect has to be taken into account in the interpretation of the pressure data. Is it possible to determine the exact altitude of the surface not using the pressure sensor, for instance, using images?
Well, I think that the pressure, I mean, when you move around do you mean when you move with the rover and you change in elevation?
Yes.
If you see an effect on pressure? Or if we take into account that effect?
Yes, yes.
I think you measure the pressure in the place where we are. I mean, if you move to a place with its higher pressure, you will detect that in the pressure sensor, the way that it works.
What I meant is if it is possible to determine the elevation difference without using the pressure sensor.
Oh, yeah, sure.
Yeah?
Yeah, for example, this is something that I've been doing, that Bob has been doing. He tried to compare with the Viking landers. Try to extrapolate that. I mean, that to change to extrapolate to the different elevation.
Another question? If not, we move to the last talk of this morning session. This talk will be given by Vicky Hamilton, and this will be about the first results of the MSL RAMS ground temperature sensor at Rocknest.
So do I get all the leftover time? The first thing I'd like to do is thank my collaborators, and in this very important part here are all of the people who do the uplink and the downlink and verify and validate the data. And they work extremely long, hard hours, and they deserve a great deal of thanks. So today what I'm going to talk to you about is focused primarily on the ground temperature sensor of the REMS suite. I'll show you what the ground temperatures are along the Curiosity traverse through Sol 100, and then I'll focus very specifically on some diurnal temperature variations we see at the rock nest site in particular. Because temperature variations vary from place to place as a function of things like albedo and season and other properties, it's hard to compare them. And so one of the things we like to do is convert them into another parameter that is independent of those environmental variables, and that's thermal inertia. So I'll talk a little bit about turning some of those temperature measurements into thermal inertia. Thermal inertia is also a proxy for effective particle size, so we can compare that to what we see from the imaging data. And then finally, I'll conclude with some comparisons to orbital data from the Mars Odyssey Themis, which is an ongoing study. So the Rover Environmental Monitoring Station, or REMS, is a suite designed to do atmospheric measurements primarily by measuring pressure, air and ground temperature, relative humidity, and UV flux. Here I'm focusing on the ground temperature sensor results. In the previous talk, you saw the configuration, the fact that REMS is kind of a distributed suite of instruments. We're on the boom 1. It points just behind the right-hand side of the rover, and I'll have some images in a moment that'll show you where it's looking on the surface. But in addition to contributing to the atmospheric science, the ground temperature sensor also serves some really valuable geologic science objectives as well. And so I wanted to especially call out the fact that additional companion papers at this meeting are going to talk about results from the other REMS instruments, as well as talking about how the different measurements from the different instruments all fit together. And especially, there will be several posters in this afternoon session. So some of the science objectives relating to the ground temperature sensor have to do with things like obtaining a detailed understanding of the energy flux and energy budget on a diurnal time cycle. Many of the orbital measurements we have are restricted to certain times of day because of those missions' priorities. Here we have measurements from every hour of the day, and that helps us understand things with a greater level of detail. We also want to characterize the surface materials and try to understand any mechanical, chemical processes that modify them over time, things like aeolian processes or chemical alteration processes that change the physical nature of the surface. We especially want to then relate the local scale observations we make with MSL to the global scale observations we obtain from orbiting platforms. This allows us to use ground truth to scale up to those global scale measurements and also give us sort of a bug's eye view of what those orbital instruments are seeing from so high up. Finally, we can use these integrated local and global observations to help us improve our predictions from the orbital data of what we might see not just along the MSL traverse in the future, but also what we might expect to find elsewhere on Mars, where thermal inertia, for example, is a parameter that's very highly sought after for understanding things like entry, descent, and landing safety at various landing sites around the planet. So the ground temperature sensor and all REMS measurements, in fact, are nominally made for 5 minutes at the top of every hour with a measurement every second. As you saw in the previous talk, extended sessions can acquire data for an hour, 2, even 3 hours at a time, giving us a very discrete but long, detailed observation set. The ground surface brightness temperatures that we're measuring here are measured by a thermopile mounted on one of those booms on the mast. The one we're using has an 8 to 14 micron filter, so we're looking at long-wave infrared brightness temperatures here. The field of view of the sensor is about 100 square meters. What you're seeing here is a NavCam image of the rover. The wheels are here. It's slightly distorted because it's a wide-angle view. This is the rear of the rover. This is a schematic representation of the area of the ground that the GTS is actually seeing at any given time. And this is the location at Bradbury Landing. One of the other things we're making sure to do is collect what we call standard classed survey images. These are images that are acquired with both the left and right mast cam, the medium and high resolution versions. And those are specifically targeted to be taken right here in the near field area of the ground temperature sensor. This allows us to take a very detailed, hundreds of microns scale view of the surface materials and compare those properties to what we might predict from the slightly larger scale temperature measurements. So trying to show you a full day's temperature curve for 100 sols is a really complicated mess. So what I've done is taken each day's measurements and simplified them. I take the 5-minute session of all of those several hundred observations and condense them to a single average value. Then I take the daytime maximum and subtract the nighttime minimum. So what you're seeing here is the delta in temperature over a single sol represented by each individual point. One of the things that's characteristic of temperature change is it's related in part to the thermal inertia of the surface. So for high inertia surfaces, very rocky materials, their total temperature change during the day is relatively smaller than it would be for a material that's dominated by, for example, dust. So what you're seeing here is you can think of this as a proxy for relative thermal inertia, not absolute thermal inertia. So as the delta temperature goes up, you're seeing a decrease in the relative thermal inertia of the materials. And so the point here is that we've definitely seen materials that have higher and lower inertias along the traverse. Now, the red pluses here are an indicator of the orientation of the rover relative to north. The reason I've plotted this is because we want to know for which 24-hour cycles we were actually looking at the same spot on the ground the entire time. If there's only a single red plus here, it means that in that sol, we moved. And so the 24-hour cycle doesn't represent the same spot on the ground. So we're looking, our initial energy is being focused on places where you see 2 or more of these pluses in a row so that we know that we have full diurnal temperature measurements for the same location on the surface. Bradbury Landing is where we started, so I just showed it here for reference, but I'm really going to focus on Rocknest today, and I'm especially going to focus on measurements out here at Sol 100. I will point out quickly that the dust storm that Javier mentioned in the previous talk set on around Sol 93 or so, and you can actually see that whereas the daily temperature variations up here were within sort of 4 to 5 degrees of each other, all of a sudden we start seeing a drop in that, and that's probably due to the increase in atmospheric opacity. So to zoom in on the Rocknest sand shadow, you can see the sand shadow here. The ground temperature sensor field of view extends a little bit beyond the sand shadow to include a few little scattered rocks out here, but the majority of it is dominated by the sand shadow itself. We spent about 40 sols here, and the reason was because we needed to clean out the sample handling system, and we wanted to exercise SAM and Chemin for the first time. So what that gave us was a really wonderful long time series of data at the same spot. These curves here are the diurnal temperature curves measured by the ground temperature sensor. Each hour has a data point, and that's just the average of that 5-minute session. What you can see as time goes by here and the season is changing, the curves are basically shifting upwards ever so slightly. This is consistent with the warming that comes on with the onset of southern spring. The uncertainties associated with this instrument are greatest when it's very, very cold, so you'll see the greatest deviations from a consistent behavior in the very late evening and pre-dawn hours. The other thing I'll point out, but I'm not going to talk about today, is that we see some variability here in the afternoon and evening cooling rates, and we're still trying to figure out how much of that is real, how much of that is signal to noise, and trying to separate all that out. Now, trying to, as I've just pointed out here, as time goes by, trying to compare temperature variations over time can be tricky because there's seasonal effects. And so we really want to try to remove those effects. And the way we do that is by converting temperatures to thermal inertia and predicting thermal inertia for the locations we're looking at. So thermal inertia, as I mentioned earlier, is also a proxy for particle size because thermal inertia is dominated by the conductivity of the material. The model I'm going to use here is the KRC thermal model developed by Hugh Kiefer, originally for the Viking IRTM dataset, but it's subsequently been used with the Mars Global Surveyor Thermal Emission Spectrometer, the Mars Odyssey Themis, and the Mars Exploration Rover's mini-test data, so this is a long heritage model. Basically, the way it works is that the user provides information about the local environmental conditions, things like your elevation, your latitude, what is the albedo, all kinds of things that factor into the daily temperature variations. The model takes those along with a guess, an initial guess at the thermal inertia, and it gives you back a predicted kinetic surface temperature. And so we do this iteratively with different guesses at the thermal inertia until we converge on a solution that gives us a kinetic temperature that's very similar to the brightness temperatures we've measured. For right now, we're not worrying about the actual difference between kinetic and brightness temperature. The brightness temperature should be probably slightly less than the kinetic temperature due to emissivity of the surface, as well as the imperfect transmission of the filter. On the other hand, the rover radioisotope thermal generator is providing heat to the scene, so it's helping to increase a little bit. But these differences probably only total on the order of 2 to 3 Kelvin. So that's not anywhere near enough to really make a substantial difference in the thermal inertias that we extract this way. So here I'm showing the ground temperature sensor measurements in yellow for Sol 100 at Rocknest. The uncertainties here are just the 1 sigma standard deviation on the averages for each hour. When we run the model, the thermal inertia that best fits this curve is one for a material with a thermal inertia of about 250 SI units. That thermal inertia is consistent with a homogeneous material made of medium sand-sized particles. So these are particles 250 to 500 microns in size. And I want you to try to remember that when we get to the next slide. I'll also point out that the modeled profile here is a little bit narrower than the actual measured daytime profile. And we're not entirely sure why that's occurring yet. We don't know if it's quite a real effect. There might be some more tweaks to be made to the thermal model there. But it's very possible that there is something causing the surface to warm up a little bit faster than the model predicts and stay warm just a little bit longer than the model predicts. Lastly, there is this little deviation here from the model, which might be perceived to be some sort of anomalous afternoon cooling. But on this particular sol, we did bump the rover ever so slightly, and so our orientation did change a little bit, and it's not impossible to rule out the effect of a new field of view on that particular sol. So to give you a sense of how that thermal inertia prediction of the particle size compares to what is actually there, this is a class survey image from the Mastcam 34. This is a MOLI image of the Rocknest sand shadow, and what you can see is that this is an incredibly homogeneous looking surface. When you trench into it, however, and as described previously, you see that the upper surface is dominated by much coarser particles than the interior of the sand shadow. Those upper surfaces are dominated by millimeter-sized grains that should have a thermal inertia of somewhere between 3 and 350. The 150 micron grains in the interior, on the other hand, should have a much lower thermal inertia, somewhere in the order of 180 to 200. Now, on the previous slide, I said that our fit to the diurnal curve from the ground temperature sensor predicted a thermal inertia of about 250, which is right in the middle of these values. The thermal skin depth for a material like this is actually on the order of a couple of centimeters. So we're being sensitive to the properties in both the very surface as well as some of the subsurface. And what we're essentially getting is mixing. And this is entirely possible with thermal inertia because thermal inertia is not a unique parameter. So finally, I'll wrap up by talking about comparisons of our ground temperature measurements with measurements of temperature made from orbit. And what I'm comparing to here is the Mars Odyssey Thermal Emission Imaging System, or THEMIS. Now, this instrument has 100 meter per pixel resolution, so it's viewing a much, much larger area than what we're observing with MSL. THEMIS flew over the MSL site on the afternoon of Sol 100. The temperature from band 9 of that instrument, a 1 micron wide band around 12.5 microns, compares very well with the ground temperature derived from the ground temperature sensor. They're within 7K of each other. We haven't made any attempt to correct either data set yet for little things that might subtly change those temperatures, like the emissivity and all that, but the emissivity would be the same for both things because we're in a very, very dusty area. The other thing I'll point out is that THEMIS does make measurements at several times of day. The orbiter started in a terminator orbit. It subsequently, in a very high-level view of the time of local time, changed to a much earlier orbit around 3 p.m., and now we're swinging back towards the terminator again. So we actually have the ability to collect data from about 3 to 6 a.m. and 3 to 6 p.m. historically, and then again in the future. So this comparison was from an afternoon measurement, and we have measurements that we're collecting at other times of day as well. I would compare the Themis thermal inertia to the ground temperature sensor thermal inertia if we were looking at another location. Here, the ground temperature sensor was looking at this aeolian feature, a very small scale sand shadow. That sand shadow is not characteristic at all of the broader area that Themis was looking at. So the Themis thermal inertia is actually quite a bit higher, and it wouldn't be fair to compare the two. But that is one of the things we're looking at along the traverse, is looking at the broader scale variations in thermal inertia and how they compare with the orbital data. And then as a last thought, I'll leave you with the idea that one of the things we're really making an effort to do is make sure that every time Themis flies over the site, we're collecting new images, be they more at pre-dawn or afternoon images. And when we do that, we're also collecting those extended REM sessions, because right now, for example, Themis is in a roughly 4:30 orbit, so a 4 o'clock and a 5 o'clock measurement wouldn't quite capture the time of the overflight, so we're making an effort to get extended observations from 4 to 5 so that we actually include the time of that overflight. I want to wrap up here. I have no conclusion slide on purpose, because this is very much an ongoing experiment. It's a long-term, long-duration experiment, and will have its greatest results by looking at observations over time and comparing those as we go along. Thank you.
Thank you, Vicky. Questions for Vicky?
Everybody
No
wants
questions?
lunch.
Bernard?
When you get close to 0 degrees C, do you expect some changes in thermal inertia, for instance, linked to the deposition of water? And so would you think that this should be put into the fitting of the thermal inertia, not a single value would be able to represent the transition around 0 degrees C?
So if I understand your question, you're asking if when we get down to the freezing point of water, we should be changing the model to account for that. Historically, no, this model takes into account the freezing point, the condensation point of CO2. But I believe, if I understand the model, how the model is actually working correctly, and as well as the physical processes, first of all, we're at the equator. There is no ground ice stability predicted for this location as a first factor. But one of the things that could be considered, for example, in locations like this, one possible interpretation for this, I won't say it's an agreed upon interpretation, is that this could actually be some sort of vapor deposition process going on. Mm-hmm. So that's something that we're looking at.
Okay, thank you.
Other question? If not, I would like to thank all speakers of this morning session, and we recombine at 1:30 this afternoon. Thank you.